at the chief ore and other ores. We look at the chemical process that is involved in the extraction of that metal, and then the uses. So probably we may look at what is an ore. An ore, these are naturally occurring rocks that contain metals, that is sometimes free metal, or sometimes metal compounds in which insufficient amount to make it worthwhile extracting them. So sometimes we hear of some places in Kenya where we have metals like gold, but we don't have large-scale extraction of gold in Kenya. And the reason is because we find it in a limited amount. So it is not economical to mine those metals, even if they are expensive, but they are in a small amount or limited amount. So we may end up spending a lot of money extracting these metals, and in return, we don't get the profit. So that's why for some metals, because they are in low amount, we don't do large scale, or that's why we don't have large scale extraction of such metals. But in case we have metal carrying large quantity, then we go for industrial process, and that ore or that rock that have that sufficient amount is called the chief ore. Although there are other minor ore, but those other minor ores probably have less compared to what we refer to as the chief ore. Before extraction, factors to determine, that is the method to use to mine that rock, which is now later taken for further processing so that you can extract your metal. So which are these factors that you can determine, that determine the method that is used to mine this ore or to mine the rock that is having the metal? So the method to use depends on the location of the ore, whether it is on the surface of the earth or deep in the earth crust. So some of the methods that are used are open cast, deep shaft. So sometimes if the metal is on the surface, your time to tunatumia open cast. Deep shaft when the hole is in the deep in the earth crust. So I know some geographers maybe can tell us more methods of mining. Do you have other methods of mining? Geographers, najua mmesoma somewhere. Methods of mining. Kuna ingine apart from these two? Open cast, ikiwa surface, deep shaft, ama further clarification. Haya. Tumesema tafadhali tutumie majina official. Like techno. Who is techno? Haya, mute yourself.
There is spanning, there is dredging.
Okay.
Those are for mining deposits of ores in alluvial, like in Madish. Yes.
Yes, thank you. Any addition, Motira? Well, but Moshira, any other addition?
Adit mining, the adit method.
Yes?
Using adit, the adit method.
Using adit. So I think we have several other methods in which we mine the rocks that bears the metal. So after we have now mined that ore, we take it now to the processing stage, but there is what we call the pre-extraction process or the pre-initial stages of extraction. Sometimes when we use those methods of mining that hole, we may get unwanted matter. Maybe there could be soil, there could be dust, maybe wood particles. We therefore need to remove those impurities. We may refer to them as impurities. And as I was saying, this is the initial stage of extraction before the chemical process. The reduction or the removal of impurities from the ore, the process is referred to as concentration of the ore. In other words, you are trying to increase the concentration of the ore by removing the impurities such as soil, sand, etc. The concentration of the ore may involve there is washing with water. Sometimes there is mud and so forth. So you may wash with the water. Then there is use of magnetism. For example, if the ore is magnetic, for example, the ore of iron, we refer to it as magnetite. There is another one called hematite. We use magnetism to separate it from the impurities. There is electrostatic precipitation. That is in case there is a, you can remove dust. We are familiar with that. Then there is a froth flotation. So for froth flotation, we shall discuss it into details. It is a method that is used to concentrate the sulfide ores. They are ores whereby they are compound of sulfur. We refer to them as sulfide ores. Example is like copper pyrite, formula CuFeS2. There is a zinc blende, which is zinc sulfide. There is a galena, which is lead sulfide. So froth flotation is a method that is used to concentrate the sulfide ore. So tutaangalia froth flotation and copper, lead, and zinc. There is another method that is not included here that is called chemical treatment. So you may put that down, chemical treatment. This is applied to the ore of aluminium that is called bauxite. In the process of extraction of bauxite, the chemical treatment involves treating the ore with a chemical. In the case of aluminium, huwa tunatumia hot concentrated sodium hydroxide or potassium hydroxide. The fact that the ore of aluminium bauxite, aluminium hydroxide, hydrated aluminium hydroxide is amphoteric. Aluminium hydroxide, it is amphoteric. It is able to react with sodium hydroxide. So here tutaona in the process there is a removal of impurities. Tutaona how those impurities are removed. So it is therefore important to note kwa kila sorry for that. For every metal, lazima tuone the impurities which are there, and under chemical process tutaona probably how we remove these impurities because some of them hazitaweza kutoka. Just a moment. Okay, so let's continue. As I was saying, it is important to note the impurities that are there in each metal, because in an exam, we normally ask students to explain how the impurities are removed. That is in each metal, so it is important. So in the next part, we are now going to look at the first metal, that is sodium. Look at the occurrence of sodium. We have sodium occurring as brine. That is a solution of sodium chloride, and that is found in salty seas and ocean. We have rock salt, which is solid sodium chloride. Rock salt is the chief ore of sodium. This is the rock that we use to now extract this sodium metal. Then we may have it from trona, and you know trona is a double salt. Then we have another one we call shell salt petra, which is a sodium nitrate. Sodium nitrate can also be an ore also. So these are sources or ores of sodium, but the main ore I've said it is rock salt. So we shall be looking at the chemical process of extraction of sodium from rock salt. There are two types of extraction that is under chemical process. There are two chemical processes that are involved in the extraction of the metal. And the two methods depends on the reactivity of metals. We have electrolytic method. We know one application of electrolysis is extraction of metal in form 2. We discussed under application of electrolysis is used in extraction of metals. Electrolytic method used in extraction of metals. Electrolysis, we use this method in the chemical process when we have a reactive metal. For example, sodium is a very reactive metal. It can also be applied to potassium metal, calcium metal. So in this case, we shall look at sodium, aluminium. Those two, mainly we shall discuss electrolytic method of extraction of these two metals. We shall also see that zinc can also be extracted using electrolysis. The other method is applied to moderate or less reactive metals. That is reduction method. This is where we reduce the metal oxide using reducing agents. Most common reducing agent is carbon and carbon 2 oxide. So there are two categories of chemical process that are involved in extraction of metals, depending on the reactivity of metal. Electrolysis, tutaiangalia under sodium, aluminium, and we shall also discuss zinc. So for sodium, the electrolysis cell, or where we carry out that electrolysis process, it is in a structure that we call the Downs cell. From that, we get the process, Downs process. So what do we require? The raw materials, we have rock salt, the solid sodium chloride. We require calcium chloride. Then we look at the chemical process that is involved. The first thing is to make sure we melt this solid sodium chloride. The melting point of this sodium chloride is 800 degrees centigrade. And here comes the use of calcium chloride. A little calcium chloride is added to lower the melting point of the electrolyte to about 600 degrees centigrade. So this is economical because less electricity is going to be used. Calcium chloride is acting as an impurity. The structure, that is the down cell, is made up of steel, but on the outer part, we have fire bricks. Fire bricks, I'll give an example of a jiko, ile yenye tunatumia kuweka makaa. On the inner part of that jiko, we have a lining. Ile lining yake pale ni most of the time inakuanga heated clay. Heated clay inawekwa pale, kazi yake ni ya to prevent heat loss, you know, to conserve heat, prevent heat loss and conserve heat. So in the structure tutakuja kuiangalia, the work of the heated bricks is to conserve the heat, that is ensuring now the molten sodium chloride stays in that molten state. The fact that the fire bricks is used to conserve the heat and prevent heat loss. So the temperature is maintained, whereby sodium chloride will exist as a molten state. So the fact that we have also added the calcium chloride during the electrolysis process, also this calcium chloride is going to be electrolyzed. That means we also have, two metals in the process. We shall obtain our calcium in the process and sodium in the process. So have in mind how the arrangement of electrolysis setup look like. There is that one in Form 2, which is a very common electrolysis of lead 2 bromide. Heat must be there. There is electrodes, mostly made up of graphite, that is carbon. There is the source of the current, and we normally label these electrodes as anode and cathode. We know that anode is positive, cathode is negative, and the reason is because what determines whether the anode is positive or negative, or the electrodes is positive or negative, is the terminal of the battery that is used there. If the anode is connected to the positive terminus, that means that anode is a positive. So don't confuse this with electrochemical cell. In electrochemical cell, where oxidation was taking place, that electrode was the negative terminus. In the electrochemical cell, where oxidation, remember that half cell that we started drawing on the left side, that half cell, the electrode is forms the negative terminus. The electrochemical cell is now the source of the current. So the negative terminus is where oxidation is taking place. So what about this electrolytic cell in the down cell? So you have the anode, we have the cathode. So let's look at how the structure looks like. The molten electrolyte is electrolyzed in carbon anode, that is the carbon graphite anode, suspended at the center, surrounded by a steel cathode. So the anode in this cell is made up of graphite, while the cathode is made up of steel. So tunasema that the anode is the positive, yes, and the cathode is the negative. So which reaction takes place in the anode? Is it oxidation is it reduction? Remember, we are looking at preferential discharge of the ions. So in this molten sodium chloride, we have which ions? We have sodium ions and we have the chloride ions. So I'm asking, which ion is going to be discharged in the anode? Which ion is going to be discharged at the anode during the electrolysis process? Maybe someone can raise hand. Is it sodium ions? Is it chloride ions in the anode? Hi, Brian.
Chloride.
The chloride ions. The chloride ions are going to be preferentially discharged in the anode. The chloride are negatively charged, and that means they are attracted toward the anode, which is positively charged, and therefore the sodium ions are attracted to the anode. Sodium ions are positively charged. They are attracted to the cathode, which is negative. So in a positive, inaenda for negative. The negative ion inaenda for positive electrode. So that means we shall have two products. That is the chlorine gas will be liberated in the anode, where the sodium is going to be liberated in the cathode. So it is important for us to be able to know how to write the half ionic equations for the reaction taking place in the electrode. So let's study this electrolytic cell, the down cell, the Downs process for extraction of sodium from rock salt. So note the various parts of this structure. So let's first of all look at where we have the electrodes. I have this electrode labeled as negative. That automatically becomes our cathode. So there is on this left side, and there is the other side, that is the right side. We also have this terminal, that is our also cathode. Then at the center, we have our anode. At the center, we have our anode, which is a positive electrode there. Note what it is made up of. The anode, we have said the anode is made up of graphite. Well, most preferred material for the cathode is steel. It is made up of steel. That is the most preferred. In most of the questions you'll get, they'll be asking of the materials that makes the anode and the cathode. So for the down cell, anode graphite, and there is a reason for that. And then the cathode steel. So avoid carbon graphite. It's supposed to be steel. It's supposed to be steel. Question, Shem?
Yes, excuse me, sir. Why is the cathode made of steel?
Okay, so but the reason why carbon is made up of steel is because one, it is inert, does not react, it will behave as a graphite. The choice of the material that makes the electrode is important to note because it should not react with the product of electrolysis. So the product that is given or that is produced in the cathode is sodium. So sodium does not react with steel. And then at high temperature, steel is stable. So inert, and it is also stable at high temperature. But for the anode, it cannot be made of steel because we know steel is that impure iron, iron mixed with other elements. Why do you think anode cannot be steel as the electrode? So probably hiyo ndio swali sasa tunafaa kuuliza kwa exam, ama ndio tunapata kwa exam. Kwa nini sikuwe imetengenezwa na steel? That is the anode. So remember, we have said in the anode, the chloride ions are attracted and are preferentially discharged. And as you can see, there is that chlorine gas that is being liberated from this opening here. Chlorine can react with steel, okay? Because steel is iron or impure iron. So that's why the anode is not made up of that steel, because chlorine produced is going to react with that steel. And we don't want that because there are some uses of chlorine. And for example, in large scale manufacture of HCl acid, huwa tunasema source ya chlorine is electrolysis of brine. And in this case, electrolysis of also rock salt. So note there is this other structure that we call the steel diaphragm or the gauge. Kuna swali? Mwashira?
Yes, excuse me, sir.
Yes.
When writing the half-cell equations, why the sodium, will you write it as liquid or as aqueous?
Now, because we are dealing with molten substance, we normally use liquid as state symbol. We use liquids as state symbol. But for aqueous, that is, for example, brine, you use state symbol aqueous. That is for solutions.
Thank you.
Okay. So, so I was saying, look at this structure, steel diaphragm, and where it is situated. So from the top up to the bottom of that cell in both sides, it is encasing the anode. The purpose of steel diaphragm, as we shall see, and this is a common question that we ask, is to prevent chlorine and sodium from recombining. Prevent sodium and chlorine from recombining steel diaphragm or steel gauge. It is made up of steel. Then note where we are adding our molten sodium chloride with a little calcium chloride. So that means whatever we feed here, it is the molten form. So that means there is a place where we first of all heat this molten this sodium chloride to melt it. Ikisha melt, najua sasa itakuwa mixture calcium chloride na sodium chloride. So tunaiweka pale kwa ile down cell ikiwa in molten state. But we can see where we are correcting our molten sodium. So it is either on this side or on the other side where we also have the cathode. But again, we have calcium, which is that molten mixture. So it is also going to be discharged in the cathode, same as sodium. So we are going to correct molten sodium and molten calcium. One, they are metals and they do not react, but they separate. How do you think we can separate the molten sodium and the molten calcium in this extraction process? Okay, yes, Jack. Yes, Jack. So we use the concept of density. That is correct. I've used the concept of density. Which one is denser? Which one is denser? Yes. Calcium is denser than the sodium, so that means sodium will float on top, then calcium will be at the bottom. So has it a mix, they will be able to separate because of the density. So sometimes we ask that concept there. Let's look at the equations. That is for the half cells, for the cell. And we shall look at it in form of equations. So we are supposed to write the equations for the decomposition. The equation for the decomposition. First of all, when we put it in a cell, we have the sodium ions and the chloride ions. They are being attracted to the electrodes. Note that there is absence of water. Hiyo ndio swali tulikuwa tunaulizwa pale. Then the two ions that are there that move to the steel cathode, sodium, in the carbon graphite anode, tuko na hiyo chloride pale. Then we are supposed to write the equations. So kindly